Hello everyone and welcome to Mathify. Today I am here to discuss some interesting problems of number theory and algebra with you all. I will write down certain problems on the board and you can pause the video to give these problems a try yourself. After you have tried, you can play the video to continue watching the solution or to verify your answers. Okay. Each and every problem which I write will be aimed at teaching you certain important concepts of the mentioned topics. Okay, so let me write the first question down for you. Okay, so the first problem reads as follows: determine the set of integers n for which n square plus 19n plus 92 is a square. An easy problem to start with. The problem is from the chapter number theory, so feel free to pause the video and give it a try yourself. Okay, so let me give you a solution for this. So first let me assume that the given expression is a square of a positive integer. Let's say m. Okay, I have assumed that this expression is the square of this m, where m belongs to positive integers. So this is the representation, you might be knowing it. So what I can do is I can use the quadratic formula to solve for n from here. Okay, I can transpose m square to LHS and then I can say, okay, so minus b plus minus root over b square minus 4ac by 2a. Okay, so this after calculation yields. Okay, so now here we have to do a very small analysis, and this analysis will be the ultimate end game, you can say, of this problem, that n has to be a positive integer. For n to be a positive integer, the expression inside the square root must be a perfect square. Okay, for n to be a positive integer, the expression inside the square root will be a perfect square, otherwise n will be an irrational number. Okay, so I can assume that this expression is equal to another constant, let's say k square. Okay, then what I can do is I can transpose, I'm sorry, it is minus 7, then I can transpose k square to LHS and 7 to RHS, and I can write 2m plus k, 2m minus k is equal to 7. Okay, now 7 is a prime number, therefore it can have only one decomposition, which is 1 into 7. So arbitrarily I can choose 2m plus k to be equal to 1, or I can choose 2m plus k to be equal to 7. In each case, the other term, the other bracket will take up the remaining numbers. So if I choose 2m plus k to be equal to 1, then 2m minus k should be 7. Or if I choose 2m plus k to be equal to 7, then 2m minus k should be equal to 1. Okay, so let me take the first case, just like that. So let me add the two expressions to get 4m is equal to 8. So k cancels out. So I get m is equal to 2. And you can check that even for the second solution, the second pair of equations that we wrote, you will get the same answer. So if m is equal to 2, now you can just put m here in the first line. 92 is equal to m square, which is equal to 4. Now you can say n square plus 19n plus 88 is equal to 0. And then it is just factorization by breaking the middle term. And you can say n square plus 11n plus 8n plus 88 equal to 0, and n into n plus 11 plus 8 into n plus 11 is equal to 0. So n can be equal to minus 8 or minus 11. Okay, so the critical step in this thinking was that for n to be an integer, the expression inside the square root must be a perfect square. Okay, so that is what we have assumed over here. So I hope you got this answer correct, because this was a fairly easy problem. Not fairly easy problem, this was an easy problem. If you were to tag this problem, this was an easy problem. So now let us slightly increase the level of the problem slightly. Okay, the next problem reads as follows: show that 1 raised to the power 1997 plus 2 raised to the power 1997 plus 3 raised to the power 1997 so on up to 1996 raised to the power 1997 is divisible by 7. Okay, so again, please give this problem a try and then continue the video for a solution. Okay, so let me give you a solution. Now the solution to this problem would be simple if you know the following fact: x to the power n plus y to the power n is equal to x plus y into x raised to the power n minus 1 minus x raised to the power n minus 2y plus x raised to the power n minus 3y square minus and so on, alternating positive and negative terms up to plus y to the n minus 1 if n is odd. This is a very important condition, this formula is valid only if n is odd. Okay, so now let me tell you how to apply this particular expression, particular theorem over here. Okay, so we are going to start by grouping the terms from the ends. Okay, so I'm going to group the terms from the end. Plus, sorry. Okay, I will have to group the terms from the extremes. Okay, first I do 1 raised to the power 1997 and I group it with 1996 raised to the power 1997. Then I will group 2 raised to the power 1997 with 1995 raised to the power 1997, 3 raised to the power 1997 to 1994 raised to the power 1997, and then I will observe that 1997 is an odd power. So I am free to use this above formula. Okay, so I can write this to be, I can use this bracket to say it is a1 raised to the power 1997 plus b1 raised to the power 1997. I can take this bracket to be a2 to the 1997 plus b2 to the 1997 and so on. I can take an to the 1997 plus bn to the 1997. Now watch this. This is a very interesting thing, that every ai and bi is 1997. You see, so it is, so there are exactly 998 ends. So every ai plus bi is equal to 1997. You can see for yourself. 1 plus 1996 is 1997, 2 plus 1995 is 1997, 3 plus 1994 is 1997, and over here you can see that 998 plus 999 is equal to 1997. Okay, so I can say for all I belonging to this set 1, 2 to 1998. Okay, so each of these terms is divisible by 1997. That is what this says, that x to the power n plus y to the power n is divisible by x plus y if n is odd, because x to the power n plus y to the power n can be factored out as x plus y into this large expression, but the underlying point is that x plus y divides x to the power n and y to the power n. Okay, so here also ai plus bi is 1997, and for each of these brackets I get ai plus bi to be equal to 1997. So each of these brackets is divisible by 1997. So first bracket can be termed as 1997 plus k1, second bracket as 1997 k2, third bracket as 1997 k3, and so on up to 1997 k 1998. Okay, where all these k1 k2 k3 k4 up to k 1998 are integers, so I can group them as 1997 into k1 k2 and so on up to 1998, and then I can immediately say that this expression is divisible by 1997 into some integer capital K. Okay, so the key point which I wanted to illustrate through this question was that x to the power n plus y to the power n is divisible by x plus y if n is odd. So x plus y divides x to the power n plus y to the power n if n is odd. So that is the key point that you must appreciate through this question. Okay, now let us turn to some questions of algebra. Okay, so now it is time for the third question. Show that f of x is equal to x cube plus px plus q has a repeated root if 4pq plus 27q square is equal to 0. Now this is a question which requires a theorem which is not generally taught in 9th 10th standards, so do give this problem a try and then continue to watch the video for a solution. So now it is time that I furnish you with a solution. The theorem, there is a very important theorem with respect to question of repeated roots. So whenever you see a question of repeated roots, there is a very important theorem concerning repeated roots. So let me write the theorem first and explain that to you first, otherwise you won't be able to proceed in the question. The theorem states as follows: if f of x has a root repeated m times, then its derivative equation f dash x has the root repeated m minus 1 times. So this is derivative. So let me give you a proof. For example, if there is a function f of x and it has a root, let's say alpha, repeated m times, and all other roots are packed in this polynomial g of x. Okay, assume that this alpha root is repeated m times and all other roots are packed into this polynomial g of x. So now let me take its derivative. So it is x minus alpha whole to the power m into g dash alpha g dash x plus g of x into m times x minus alpha whole raised to the power m minus 1. Okay, so it is the product rule which I have applied. So first function into derivative of the second function plus second function into derivative of the first function. From these two terms, what you can take common is x minus alpha whole to the m minus 1. So you are left with x minus alpha into g dash x plus m into g of x. Okay, so you see that f dash of x has alpha root repeated m minus 1 times, and all other roots are packed inside this large polynomial. Okay, so yes, this is a polynomial. This will give another polynomial. This derivative, if you have g of x and you take its derivative, it will give another polynomial. If you multiply it by x minus alpha, it will give yet another polynomial, and when you add that to the product of m and g of x, then you will get yet another third polynomial. And if you solve that polynomial, you will get the remaining roots of f dash of x. But whatever be the remaining roots, whatever the remaining roots may be, x minus alpha will be repeated m minus times. That is guaranteed. Okay, so you have to use this concept over here. So if fx, which is equal to, in our example, xs cube plus px plus q, has a repeated root, then f dash of x will also have that root repeated one time less than the number of times it is repeated in f of x. So the derivative equation of this particular function is 3x square plus p, and I will set that equal to 0 now because I want to find the roots of this equation. So from here it is seen that x square is minus p by 3, so x is equal to plus minus p by 3. Okay, so now you might be inclined to think that this will be a complex number, but that is not necessary, because p might be negative. P is an algebraic variable, so it can also be negative. In case it is, if it is negative, then this will give a positive term, and there is not a problem if even if the root is complex, because this theorem which I have written down is valid for real roots and complex roots alike. Okay, so don't worry about that. So now I will have to say that x is equal to plus minus root over minus p by 3. Okay, so if this is a root of the derivative equation, then obviously this will be the root of f of x. Okay, so I can substitute this into the original equation, right? So this will yield minus p by 3 whole to the 3 halves plus p whole to the q to be equal to 0. Okay, so then I have to copy this expression, and I have to rub the remaining board because I have run out of space. Okay, so this is the expression that we have got: minus p by 3 whole raised to the power 3 by 2 plus p into minus p by 3 whole raised to the power half is equal to minus q. I have transposed q to RHS, and now what I can do is I can simply square both sides to remove this half in the powers. So it is minus p third whole cube, squaring both sides, p square minus p by 3 is equal to q square, and then minus p cube by 27 plus it is minus p cube by 3 is equal to q square. So I can now multiply the both sides by 27. So it is equal to minus p cube plus 9 into minus p cube. Okay, I have missed one term here. I have whole squared this, so I will also have a plus 2 p square by 9, and that will be equal to q square. Okay, so now I have to multiply this thing by 27, so which is equal to 6 p square, and that is equal to q square. Okay, so it is minus 8 and 27 q square, of course. So then I can simply p cube term. So now what I can do is minus 4 p cube is equal to 27 q square, and 4 p cube is equal plus 27 q square is equal to 0. So we have what we ought to. Okay, so now let us come to the last question for today. Okay, so now I have given you the hint that this question will also use the theorem about repeated roots. So please give this problem a try and then continue the video for a solution. Okay, so the given equation, I will denote it by f of x is equal to 0, let's say, and f of x is this long expression. So what I will do is 1 is twice repeated root. Okay, so 1 is repeated 2 times. So in its derivative equation, 1 will be repeated 2 minus 1, which is 1 times. Okay, so let me find the derivative equation of this first. It is 3ax square plus 2bx plus b. Okay, and I will set this equal to 0. 1 satisfies this equation 2 times. 1 will satisfy this equation only 1 time. So what I can do is f of 1 is equal to 0, because that is given. 1 is a root of this equation, and I can also say that f dash of 1 is also equal to 0. I have not set this equal to 0 at this moment. 1 is a root. Now I can set f dash of 1 is equal to 0. Okay, so now I can just substitute 1 over here. A plus b plus d is equal to 0 from here, and then simultaneously I have 3a plus 2b plus b is equal to 0. So A plus 2B plus D is equal to 0. 3A plus 3B is equal to 0. So from here A is equal to minus B. So from here minus B plus 2B plus D is equal to 0. So what I can say is that B plus D is equal to 0. So minus B is equal to D. So combining these two, I can say A is equal to minus B is equal to D. What we had ought to write, hence proof. Okay. So those were the 4 problems for today. I hope to see you all soon. Thank you.